Hey everyone, in this video I'm going to show you a Centroid tracker that I built in C++. So we'll start with the camera. It's a near IR camera, so it's only grayscale, and we'll show the responsivity in a second. It's a point gray camera. They were acquired by FLIR. I think they're around probably $1,500 or something if you want to buy them off of Edmund Optics. The lens right now is just a cheap $20 lens from Amazon. The application was purpose built for a different lens, so the field of views don't quite line up with the grid lines, but we'll see that in a bit. So yeah, this is the camera. It's just a USB 3 camera. That'll plug into the laptop, and then we'll be grabbing frames from the camera and processing them in real time to build our Centroid tracker. Alright, so here's a graph of the responsivity, the quantum efficiency of the camera. So it goes from 400 to about 1 micron. The demo I'm going to show you, I'm using two different wavelengths. So one is in the green, which we can see lines up with that peak responsivity for the monochrome, that gray line there around 70%, 500 nanometers. And then I do have a 1 micron laser that the visible camera won't see, but you'll see it on the IR card, and the tracker will also see it, right? So I kind of give you a side-by-side visible camera, that's just the camera I'm using right now, the near IR camera, which is just grayscale, and that's what the tracker is running on, and then we can see which of those cameras can see and track those wavelengths. Alright, so on the left we've got the visible camera, which is the same Sony camera I'm using right now. I turn on a green laser pointer. In this case it kind of emits a rectangular shape, and we can see on the tracker it's ID'd that as ID number 9, and as I move it around, the green outline is that Centroid outline, and then the black crosshair is the moment or the center of that Centroid. Now I add in another green laser pointer. This one's more circular, and we can see that it's tracking that one too, all in real time. The frame rate is about 30 Hertz right now. You can bump it up to like 60 Hertz or higher, but for the type of stuff I'm doing, a lower frame rate's fine. It's not the most robust tracker, so you'll notice that the IDs sort of jump around. Number 9's been fairly stable, but as there's specular reflections on like the Kapton tape or just the poor beam quality, the tracker will try to ID those little hot spots. So now I'm turning on the 1 micron laser, and you won't see it on the left on the visible camera, but the tracker, the near IR camera, will pick up this 1 micron. And there it is at ID 0. So we can see it on the tracker, and as I go up to the indicator card, those actually fluoresce when they're illuminated with near IR light. The two cards on the left are low power, so we can see a little red spot when the spot goes on there. But the card on the right is actually high power, and it would fluoresce like a yellowish green, but this 1 micron source is too low power to even show up on the card. But we can see for the duration, right, we've been tracking object ID 0 and 9 without any issues, and you can see some beam clipping on the 1 micron that it was also trying to track too. So the way this tracker works, and as I turn this laser off, it goes through a couple different modes and it flashes, so it's a bit messy to turn off. But the way this tracker works, it's just looking for the bright spots in a grayscale image. So there's nothing fancy about like target discrimination. And if we look at the tracker settings in the upper left, I'm only really doing 2 image processing steps. I dilate the original image, which just takes like a 9x9 kernel, and it essentially inflates the pixel values. So if there was like a really tight bundle of speckle, it's now more of a blob. And then I just do binary thresholding. So I convert it to a binary image, and I say everything above 250 on the grayscale, that's a target I might be interested in. For now we can ignore the crosshairs because those were for the other lens that isn't this Amazon lens, but that would essentially line up the camera field of view more nicely. And then, yeah, the only tracker settings are down in the lower left there, where we can set how many objects we want to track, how many frames an object could be missing. So in this case, I have 60 frames, which is about 2 seconds for 30 frames per second. And then max distance and timer interval, those are more like fine-tuning parameters for how quickly you want the tracker to update and if your target's moving more quickly or slowly. Everything was done with open source software. So the camera, now that it's owned by FLIR, they use an SDK called Spinnaker, and that's how you get the camera to read in frames via USB. But the tracking itself is all done with OpenCV and just some basic C++. So in my main application, I sort of check, does the user want to dilate the image, erode the image, or threshold the image? In this case, we only do a dilate and a threshold. So it'll run the stock functions from the OpenCV library for those two. And then I run find contours, which that's what gets us that green outline on all those different objects. And then I'll calculate the moments, which is another stock OpenCV feature. So the bulk of the tracker is actually in that last line. Objects equal, or gets the value Centroid tracker from that update function. So I essentially call the update function of my tracker on every single frame that I'm streaming in. And depending on how I want to filter data, it then updates the position of the tracked IDs. So here's another code snippet that shows what's going on inside the Centroid tracker class. So we essentially just have 4 functions. We initialize the tracker, we have a register object, and then we have a deregister object. But the bulk of everything is happening in that bottom one, which is the update function. That's the one that gets called every single frame, and we essentially compute the Euclidean distance between the previous set of points, and we try to find the closest neighbor to where that ID used to be in the previous frame. It works fairly well for slow-moving objects. It's not very robust for occlusions, right? If something goes in front or behind another one. It's not really tracking that trajectory, so it can't really predict where it's going. But for really simplified tracking where you've only got 1 or 2 objects in a scene and you want to track them quickly, that's not too expensive, right? You don't have to do any machine learning or any AI stuff that could slow down on every frame. This tracker's pretty efficient in that sense. It's only 162 lines. And from the demos, it works pretty well. So the next thing I'm going to show is essentially that binary image, what the tracker is seeing every frame. And this will give you a better idea of how it's IDing each of those components. So we've got our same 3 indicator cards, and as I do the green laser, we can see the speckle up on the Kapton tape. And then we see the spot too in the binary image. And the lag you're seeing is just kind of lag from me trying to line up all these videos to make the YouTube video. Everything is pretty much real time, so you don't notice a lag when you're moving the beam up and down. So that's the green lasers, and now I'm going to bring back in that 1 micron laser, which is really at the tail end of the responsivity. It's well below 10%, and we can still easily pick it up here, even when it's not on the indicator card, which is kind of cool. You could tweak the camera exposure and the gain settings to sort of dim everything down so that it's a lot cleaner when it's tracking items. But right now I just have everything set to continuous so that we can more easily see the background scene too. So yeah, that's the little application I built. It's a Centroid tracker. It was all done in C++. The GUI application is wxWidgets. That's a great cross-platform, open source GUI builder, basically. I didn't know too much about that, but I started watching. I'll link it in the description below. I think it's now Luke's Dev Tutorials. He does a really great job of showing you like the ins and outs of wxWidgets, how to set it up with CMake, which is super useful. So yeah, just a fun little computer app with some cameras.